All right, welcome back everybody to our Calculus 3 class notes. Okay, we're getting ready to wrap up section 15.8, transformations in multiple integrals or substitutions in multiple integrals, which really essentially means transforming the multiple integral from one domain D to another one G, where perhaps the integration is easier, or academically just understanding how these transformations work. So let's go ahead and go all the way through one with the triple integral. Let's say we have this triple integral with respect to x, y, and z. And we want to apply the transformation that u equals 2x minus y over 2. So this is going to be u. V equals y over 2. So this shows up in the limits of integration here. So that's kind of making a sense of v equals y over 2 substitution. And then we have another one, w equals z over 3. That will give everything in terms of u, v, and w. But first of all, this actually can be integrated fairly easily in terms of x, y, and z. So let me not walk you all the way through that, but take a look at it, and you can see that the answer should be 12. It's not that difficult. The integration is not that difficult. Lots of stuff cancels out. All right, let's sketch our domains first. So this is the one that we have the integral in right now, right? So we have, if you notice, and you're looking at the original integral, we have y and z going from 0 to 4 and 0 to 3 respectively. As that's happening, x is going from the function y over 2, which is a plane in 3 dimensions, and to the function y over 2 plus 1, which is also a plane in 3 dimensions. So here's x equals y over 2 plus 1 is a line down the xy plane, but z can be anything. You slide it up and down, but we're stopping it between 0 and 3, because z varies from 0 to 3. Okay, and y varies from 0 to 4. So we're cutting it off at those planes. And then the back plane, x equals y over 2 or y equals 2x. So here's that line, y equals 2x, slide it up and down. And so you can easily see we have this sort of cubical domain, sort of skewed cubical, but it's a nice rectangular domain. So what would that be in the domain G? Now remember, by making our substitutions, we're trying to find x equals, y equals, and z equals in terms of u, v, w. So we're transforming some of this unknown domain G in the u, v, w coordinate system. So really we have to figure out what is this domain G. So when we look at our substitutions by looking at the original integral, we can kind of identify u, v, and w in terms of x, y, and z. But what we do need them in is we need to know what x, y, and z is in terms of u, v, and w. So we got to perform a little bit of basic algebra. So by making these substitutions that v was y over 2 and w was z over 3, that gives you very simple algebraic equations to see that y equals 2v and z equals 3w. So those are pretty simple. Plug those back in up here for what u was, and we want to solve for x. So we get 2u equals 2x minus 2v, right? When I multiply both sides by 2 here, I get 2u equals 2x minus 2v. I plug in to here that, I'm sorry, u equals 2x minus y over 2. So that means if I multiply by 2, I get 2u equals 2x minus y, but we know y is 2v. Whew, sorry about that. So that means that if I simplify, I get x equals u plus v. Okay, then once I have those substitutions, I will need the Jacobian, but I typically like to figure out what the boundary equation should be. So for that the back plane of x equals y over 2, that just means that u plus v equals 2v over 2. So u plus v equals v. Simplifying that, I get u equals 0. X equals y over 2 plus 1, I just have a plus 1 here. So u plus v equals v plus 1. So the v's cancel. That gives me u equals 1. Y equals 0, that's 2v equals 0, so v equals 0. Y equals 4 is 2v equals 4, so v equals 2. Z equals 0 is 3w equals 0, so w equals 0, and z equals 3 is 3w equals 3, so w equals 1. So we have a nice region in the UVW plane. Cubical region, which is what we would be looking at, which is what we were hoping our transformation would show us that that's what we should have. So we find the Jacobian. Again, it's a 3 by 3. Partial of x with respect to u, v, and w in the first row. Partial of y with respect to u, v, and w in the second row. Partial of z with respect to u, v, and w in the third row. And we can easily see this simplifies to 6. And then when I make my substitutions now, if I go du, dv, dw, w goes from 0 to 1, v goes from 0 to 2, u goes from 0 to 1. This is 6. Absolute value of 6 is still 6. I have very simple integrations, and I would just let you carry those out. But it's not hard. It's a nice substitution, simple integrations, and you can see that the answer is 12, which is what we got when we directly integrated it.